Camera E207, located about 6 miles north of the launch pad, shows the growth of this plume. The first evidence of flame appeared on the right solid rocket booster at 58.788 seconds. This occurred as the main engines had been throttled up to 104% thrust and the SRBs were increasing thrust. Camera E203 was located west of the launch site and gives an aft view. The exposure was set for the booster nozzle plumes. This graphic illustrates the location of the flare. The flare was located near the aft field joint, approximately 300 degrees circumferentially, which is consistent with the location of the smoke emissions at liftoff. Within half a second, the flame had grown into a continuous and well-defined plume. At about the same time, telemetry showed a divergence in chamber pressures between the right and left SRBs. Pressure in the right SRB chamber was lower as a result of the growing leak. The plume is seen here impinging directly onto the surface of the external tank and the lower aft strut at 60.248 seconds. At about 62 seconds, the control system elements began to respond to the forces caused by the plume. As recorded on E207 and E204, the first visual indication that the anomalous plume penetrated the external tank was seen at 64.66 seconds as an abrupt change in the shape and color of the plume. This is an indication of hydrogen leaking from the external tank. At 64.705 seconds, a bright sustained glow developed between the orbiter and the external tank. Slight changes in the hydrogen tank pressure telemetry data confirmed the leak 2.2 seconds later at 66.8 seconds, when the LH2 tank pressurization system could no longer maintain its normal repressurization rate. At 72.6 seconds, the LH2 tank pressure could no longer be maintained, indicating that the leak path had significantly increased and was growing rapidly. At 72.2 seconds, the guidance system showed that right SRB motion diverged from the orbiter and left SRB, indicating that the lower ET SRB strut was severed or pulled loose. During this time frame, exaggerated steering commands and control system responses registered in telemetry data. At approximately 73 seconds, both liquid hydrogen and liquid oxygen pressure to the main engines showed a significant drop. This was followed at 73.124 seconds by the appearance of a circumferential white pattern around the ET aft region, suggesting LH2 tank structural failure. 13 milliseconds later, at 73.137 seconds, vapor was observed at the inner tank, indicative of the liquid oxygen tank failing. This can be attributed to abnormal loads induced by either the right SRB rotation at the forward attach point or the propulsive forces created by the LH2 tank aft bulkhead failure, probably both. Within milliseconds, liquid oxygen was observed streaming along the external tank. At 73.191 seconds, a flash was observed between the ET and orbiter that was immediately followed by the start of total vehicle breakup at 73.213 seconds. During the next 100 milliseconds, additional flashes occur in the SRB forward attach area. As the ET broke up, the released fluids vaporized rapidly, producing an expanding cloud of gases, vapors, and cryogenic fluid with embedded debris and localized combustion of mixed gases. No shock wave or other evidence of a violent explosion was detected in the imagery. Illumination from a combination of SRB plume radiance, reflected sunlight, and peripheral burning of gases gives the cloud the appearance of a fireball. By 73.6 seconds, the main engines were in automatic shutdown mode as a result of reduced propellant pressures. The last telemetry from Challenger was received 73.618 seconds after launch. The actual vehicle breakup was essentially obscured from view by the vapor cloud which abruptly enveloped the vehicle. Hundreds of fragments were noted exiting the ET cloud. Those identified included the shuttle main engines, the left wing, crew cabin, and both SRBs. Approximately 1 second after initial breakup, film showed the front segment of the orbiter emerging from the cloud. The nose, crew cabin, and a portion of the cargo bay make up the orbiter in this view. Nitrogen tetroxide oxidizer from the forward reaction control system provided a distinctive orange-brown color to the cloud. By 74.578 seconds, a yellow cloud or flash was visible near the orbiter nose segment. This is believed to be caused by burning monomethyl hydrazine from the forward RCS. The flash reaction from the RCS propellants abated, revealing separation of the nose section from the crew cabin. Less than a quarter of a second later, the crew cabin was noted to be severed from the cargo bay. Igniting of propellant discharge continued to be observed from the forward RCS. A camera south of the launch pad recorded a wider array of debris exiting the vapor cloud. The initial emergence of the crew cabin from this perspective was at 75.237 seconds. The initial path of the crew cabin from the vapor cloud carried it across the path of an adjacent contrail, clearly revealing its truncated form and attitude. The left wing became visible at 78.531 seconds. The main engines and crew cabin are also identifiable. After 10 seconds, the crew cabin was seen again with the front end and top of the cabin visible. As the subject moved further away and dropped lower on the horizon, the quality of the image for visual analysis deteriorated rapidly. Long-range tracking cameras followed the SRBs through range safety destruct. At approximately 75.8 seconds, the right SRB was seen exiting the cloud. Camera E207 shows the right SRB after the breakup, and the joints are clearly visible except for the aft field joint. This confirmed the location of the plume along the longitudinal axis of the SRB. The separated nose cap and deployed drogue parachute are identified at approximately 76.4 seconds. The shock wave from the detonation of the linear-shaped charge on the right SRB can be seen clearly. Simultaneously, the left SRB was destroyed. At approximately 37 seconds, Challenger had encountered the first of several expected high-altitude wind shear conditions, which lasted until about 64 seconds. These wind shears are best illustrated by the effect on the booster exhaust trails. The effect of wind shear was immediately sensed and countered by the guidance, navigation, and control system. Wind reconstructions were aided by comparing predicted exhaust trail shapes with acquired photography. The reconstructed winds were used in trajectory and flight loads analyses, which verified that the loads were within limits. Several flashes in the SSME plumes were observed during the flight. As similar flashes have been seen on several previous flights, they are considered not to have contributed to the accident. The visible condensation that appears in this frame is created by shock waves which develop as the vehicle passes through the speed of sound.